Okay, so
Is it still black?
okay, I guess we can start the. So, I think we can start the meeting. So, hello, welcome to the session, and I'm Noel Alex. Yeah, I'm Noel Alex, and I'll be taking care of the. Can you guys reduce the volume, please? Yeah, I'll be taking care of your. I'll be handling the class for today, and today I'll be introducing to you about Google DeepMind and their AI technologies. Right. So I hope you guys have heard about Google DeepMind, and if not about Google DeepMind, you definitely know about the tech. So hello, yeah, you definitely have heard of the technologies. You are probably using a bunch of them, and you are definitely interacting with them on a daily basis. However, you might not realize it. So Google DeepMind is Google's AI lab. Okay, I'll start sharing. Also, yeah, the notes that I pasted, it's an Obsidian Vault. If you do not know what Obsidian is, it's an app that is, that helps with note management. If you do use it, it helps with productivity a lot. And yeah, I mean, if you download Obsidian and then you open it up as a vault, you can see a bunch of links. It'll take you to all the notes in between. Do not touch anything else. I mean, it's all in the okay. You'll see one folder called Google AI Notes. Open it in Obsidian. You'll see there'll be another folder called Main Notes. Once you open up Main Notes, there'll be a bunch of other folders, a bunch of other files. If you want to follow along with me that way, of course you can follow along like that, or else you can just watch the screen. You can see yourself. But that is there. If you want to go into things a bit deeper later on, and I mean, maybe later it may or may not be maintained. However, it gives you a good amount of information so that you can carry on forward without any issues at all. So yeah. Okay, I'll start. I'll start with the session now. Also, about just some info about Google DeepMind. So yeah, so Google DeepMind is. I hope you can see my screen. I hope everything is fine. So yeah, Google DeepMind is Google's AI lab. It's actually like a combination of two different labs, and basically, they're pretty much the largest AI lab in the world, and the research that comes out of it has changed the world forever. In fact, okay, we'll be learning about it all in extreme detail. However, one of their papers that they have released, that is the Attention is All You Need paper, fun name by the way, that describes the transformer architecture, which we'll be learning in in detail. Okay, not in detail because okay, I'll tell you why not in detail. However, we'll be looking into that paper a bit, and it describes a transformer architecture that pretty much every modern AI model that you know uses currently. So, for example, all of your text to image uses transformer models. For example, your ChatGPT or any other large language model. Again, we'll look into these terms later. But pretty much anything that is similar to ChatGPT, where you ask it a question and it gives you an answer, all of that uses transformers. Then you have AlphaFold as well, which is another super difficult technology. AI model that you'll see, that also uses transformers as well. So that one is an AI architecture that is useful for a very, very, very wide range of tasks, depending on how you train it. And it gives you surprisingly amazing results and is highly scalable. So we look into that, and that paper in which this architecture is described has been cited. In fact, when I started preparing, it was at 137,000 citations, and by now it has already crossed 140,000 citations. So in the span of like, you can expect like 1,000 more citations every single week. And this paper was released back in 2017. So I mean, if you want the paper, this is the paper. You can just search up "Attention is All You Need," and it's just a short, simple 11-page paper where they describe the transformer architecture. Now, we can start looking. Um, I will be covering, okay, although Google DeepMind has a huge history with so many different models that they have created that do amazing things, both ranging from some things that are just, used to play games extremely well, and some other things might not, some other things that might not just be games that solve like that are helping save millions of lives or like help make lives easier for billions of people. It ranges from for through everything, right? So I'll just be covering Gemini, that is a large language model, Gemini, and AlphaFold. And if you do not know AlphaFold, I'll be going into it deeper, obviously. However, just an introduction to AlphaFold, just so you know. When I chose this topic, um, I just found AlphaFold extremely interesting because it did something that seemed nearly impossible. In fact, everything that we learned today, when you look into the details of it, it is something that should not exist. Like in my opinion, it's just straight up magic how we tricked rocks to be able to think or do such magical things like this. But it's able to do all these things, right? And that's the magic of AI, and that's the thing that interests me so much. So I hope that a little bit of the interest goes on to you as well. And everything that I'm going to explain, it is super duper simple. It's super easy. If I, um, yeah, if something that I'm saying is not completely like, it's not very intuitive, if you do not get it instantly, I apologize. It is probably my lack of knowledge because everything, trust me, is super simple. Look into the notes, look into it yourself. What we're going to be discussing is about basically about ChatGPT, Gemini, right? If you do not understand anything, go and ask it themselves. You can go and ask ChatGPT what this means. You give you a beautiful answer, and that is something that should shock you as well. That me, after trying for so long, still cannot match something that can be explained by ChatGPT so well, right? So let that be, your hands-on experience with this as well. So yeah, Google DeepMind is pretty much, as I said, Google's AI lab, and they have been working with AI technologies for many years now. And okay, it's headed by Demis Hassabis. As I said about AlphaFold, right? Demis Hassabis, along with another researcher from Google DeepMind, along with David Baker, another scientist, a biochemist, basically. They three collectively won the Nobel Prize for chemistry this year as well. So and that too they won it for for AlphaFold as well, the technology that they created with Google DeepMind. So yeah, so it's headed by Demis Hassabis back in 2010, and since then they have been working with many different AI models. Some of them include AlphaGo. So AlphaGo was the first AI model that was able to beat a Go champion. And Go is an extremely complicated game. It has so many different states that it can have. So it was thought to be pretty much impossible for a normal human being to beat, for an AI model to beat a normal human master at it. However, Google DeepMind, as you will see, as they started this trend of like doing things that seem impossible with AI. So it started off with AlphaGo, and then they have many more things. For example, Alpha Geometry, which is an AI math model that can solve mathematical problems on par with Math Olympiad gold medalists. So they are pretty much the best in the world, equivalent to the best in the world in the field of math as well. And also, if you want to look into their code, and if you want to look into their code specifically, they have a huge number of open source projects available on their GitHub. You can just search up their name on GitHub. You can see the code for all of it. Do that later, obviously, after the call. But yeah, if you want, a lot of stuff is available on GitHub. And I find that amazing that companies are willing to give back a lot to the general public, so people can use it and learn from it themselves, like directly with how they developed it. So yeah. So so they also have Imagen. So Imagen 3 is pretty much their text to image model. They have Veo, which is their text to video. However, Veo is not available yet. But yeah, it is their text to video model, and we have heard about Sora, right, from OpenAI. So it is pretty much Google's counterpart, and AlphaFold. Okay, so Gemini and AlphaFold will be our topics for today. So yeah, so we'll start with Gemini, and it's Gemini and the Astra project are really interconnected, and you'll see why. The Astra project in general, it's basically Google's vision of what AI should be. That AI will basically work to make life easier for people, right? So it should be able to do many different things. For example, I remember just a couple years ago, you could ask ChatGPT 3.5, the modern version of the initial version of the modern version of ChatGPT, I would say. You could ask it simple questions, could give you some answers, right? Not okay. It's very useful. However, it's not very spectacular, right? Not very fancy. So um, basically, the Astra project is that you can use AI to make life easier for many different people, right? So I'm pretty sure you guys have heard of Jarvis, right? The AI that helps out Tony Stark in his missions. You ask Jarvis to do something, and instead of just telling you what to do, it would actually do it for you, right? So Astra is pretty much that. So if I have, let's say, a camera, then I walk around and I ask, okay, what is this thing? Is this a healthy food item? How much protein is there in this meal? Possibly. All these questions, if I ask Astra, you should be able to tell me some of this info, right? So, I mean, if I ask an AI model, right, that's the goal with Astra. And pretty much a lot of this is incorporated into Gemini. And Gemini is an amazing, again, chatbot, you could say. But however, it's more than a chatbot. Again, when we go into this in more detail, you'll understand why it's more than a chatbot. But yeah, so Gemini, as if you ask it to create an image, it'd be able to create you an image. If you ask it to, maybe if you give it a YouTube link and ask it to generate notes or summaries or whatever, it's able to do that for you. If you give it some sort of like video, I mean like audio input, is able to do that as well. And okay, maybe okay, just keep this point in mind. There's something called a context length, right? So the maximum length of a message that you can give a large language model. So let's say you ChatGPT, if I copy all of like let's say Harry Potter, okay, very large books. Okay, if I copy all of Harry Potter and I put it as one question to ChatGPT, okay, I put all of it, and at the end I ask it a question related to the story, it'll probably not be able to. And like let's say that specific part is related to some, it's there somewhere mentioned within all of that huge amount of text, right? It probably won't be able to go through all of that because it has exceeded its context length, right? So the maximum prompt size that you can give a LLM or a chatbot is called its context length. Okay, newer modern models can have anywhere between 32,000 to 128,000 tokens. What are tokens? We will go into that in detail. But just for now, keep in mind that they are basically bits of a sentence, right? So let's say you have a sentence. We split it into words. However, a large language model can split it into words or even parts of words. So let's say I have a word called uh, preheat. So heat is one part, pre is one part. So an LLM might tokenize it into pre and heat separately. Or it might take another word, let's say the word, I don't know, pan. Okay, so let's say it takes pan as one token. So a token can be part of a word, more than word, but on average, a token would represent around 0.75 words roughly, so a bit like three quarters of a word, right? So most modern large language models have a context length of 32,000 to 128,000 tokens, whereas Gemini came out and in experimentation it had a context window of up to 10 million tokens, which is absolutely mental. uh, I'll tell you the challenges with why these extremely large context windows are pretty much impossible, and what Gemini pulled off is surprisingly absurd. Seems like pretty much impossible. However, they have done magical things that we will never see, so that we can have convenience as well. So yeah, although I said 10 million tokens, you cannot use that entire context window. Even if you do pay for it, you can use up to a max of 2 million tokens. However, that is still like absurdly huge compared to anything that any other large language model gives you. And in fact, there's an ongoing challenge. If you know Kaggle, the website where you um, Kaggle is a website that data scientists or machine learning scientists are very familiar with. There's a contest hosted on Kaggle right now, and that contest has a prize pool of about $100,000 each. First, second, third, and fourth, they all of them have like $100,000 prize pool. They all have 25,000 split across them. Not split across them, 100,000 split across them into 25,000 each, where basically they give you Gemini and they're asking you, it has a context window of 2 million tokens. Let's see if you can like stress test it. Like make like you think of some creative way or some actually useful way where you can somehow overflow the 2 million tokens. And that is a challenge. They're basically paying you money to see if you can overuse their product, like if it is theoretically possible. And it's not a small amount, it's $100,000, right? So yeah. So what is Gemini exactly? Um, okay, so we have heard about Gemini, we have heard about all these models. We cannot download them. However, there are these smaller models that we can actually download. In fact, there's a site called Hugging Face. One second, yeah. So Hugging Face is a site where you can download these models and you can work with them like on your own. Say, let's say if I go here, if I want to search for, let's say, some open source model. Okay, Llama is a good example. So yeah, if I talk about this, okay, Llama Nematron. okay, this is 70 billion parameters. We'll talk about what a parameter is exactly. Okay, this is a large model. I'll search for something a bit smaller. Okay, so this one, right? I can download it onto my system and I can use it locally. And this one, I think its model weights, it would be around 4 plus 5 plus 5. That's like what, 15 plus another one. That's what, 16 GBs, right? So this 16 GB file is now able to answer me questions on pretty much anything, right? How is that possible? Right. It doesn't make sense to me. That's one of the questions. That's one of the initial questions that I had regarding say LLMs. These AI models. How is it able to store so much info, like maybe petabytes of info, like the entire internet, into just 16 GBs, right? So I can download it onto my laptop and use it interactively, right? Our brain is tiny, right? We have our brains in our head. However, the amount of info that I store in my head it's insane, right? I have maybe 18, 19 years of memory, and like all of that is in ultra 8K HD or whatever. It's in super high resolution, and like I can, if you ask me to speak, I can speak for hours at a time, not an issue. I'm able to I'm able to recollect absurdly huge amounts of stuff. I'm able to imagine so many different things. I'm able to create almost an infinite amount of data out of one mind, right? And my mind is tiny, right? Even if I had, if you have seen these, basically these labs where they create chips, or you could say SSDs, hard drives. We have extremely compact storage where I can have an entire terabyte of storage on an SD card. That SD card is so tiny. If you filled my entire skull, right, so the size of my brain, with those type of extremely high compact storage, it would still be so tiny compared to the actual amount of like storage my mind has, right? So why is it so? Now the difference lies in the details, right? Your brain doesn't actually store all that info. What does it do? When you require something, it basically creates that info for you, right? For example, when I speak to anyone, or when I'm talking to you guys right now, it's able to create that info, create those words out of my mouth, out of thin air, right? That is why it has seemingly infinite storage, whereas because it doesn't actually store that much info, the storage is very little. However, with that stored amount of info, it's able to generate nearly an infinite amount of info given energy, right? And I eat food, and I'm drinking water, I take care of myself, and it's able to, okay, that feeds my brain, and my brain is able to produce knowledge, right? So this is what so again, this is okay, when you talk about AI, machine learning, neural networks, these are terms that you commonly hear. The word neural network itself, neural stands for your brain, right? It's related to your brain. So the reason why these things are related, like, have a lot of connections to your brain, is because every single network that you do is basically trying to simulate your brain, right? Because the problems that are solved by AI or machine learning, deep learning, all these things, the problems that they solve are things that we can do sort of easily, right? Only thing is we are not that fast with it, but we can all do it, right? But we have to sit and do it one by one, which is expensive, time consuming, all these things. So we are trying to automate that process, right? So now the reason why we created AI is to basically replicate a human brain. So I hope you guys have an idea of what a neural network sort of looks like. In short, let's search up a picture, neural network. So this is like the very, very, very standard picture that you would see. So you would have your input layer, then you'll have a bunch of hidden layers, and then your output layer. This is in fact how your brain also looks. Okay, in a way. Okay, obviously not exactly the same, but like similar. As in, what it does is your brain, it is a big connection of neurons where each neuron is interconnected to each other. So you have some input, right? So let's say I see something. So I have my bottle over here. So I see that's a bottle. It's quite large. It is filled with water. It's pink. I see a lot of different things. When I see it, the input is taken from my eyes, right? So now those inputs are now sent to my brain. It activates a certain set of neurons. Okay, as in when let's say the color is pink, right? Let's say the color pink is encoded in some sort of a way where it activates a certain set of neurons. Now those neurons are connected to other neurons, and those neurons are connected to other neurons. So let's say this is one neuron. So this neuron is connected to so many different neurons. And these neurons are also connected to their own set of neurons. And it keeps going on and on and on. And basically, this input, let's say this input represents the color pink. Okay. It's not, okay. This is a very small version of a neural network. We'll see later on. But this is a very, okay, let's say this part represents pink. When you, okay, so all these input, so now that value, right? So let's say, okay, somehow, God knows how, this one in your brain, right? God knows how in your brain. So your input neuron is now able to send a signal to all these other neurons, and those neurons communicate with other neurons and goes on, and somehow at the very end you get this. Let's say you in the output layer, right? There are many possible answers that you could get. For example, when I see something, it could have, my brain could say that it's black, brown, green, whatever. However, all of those other options are wrong, right? However, but with the specific set of inputs that I've given it, it goes through this entire mesh of connections. It activates different neurons. It might deactivate some of the neurons, and based on all of that stuff, finally, my brain says this specific input that I've gotten has to be pink, right, or any other color that I see. When I see a car move, I get so much info about that car, right, through my head. So many different things. Maybe the make of the car, the size of the car, how fast it's going. So many different questions you can ask. All that stuff is now encoded in my brain in this sort of a manner, right? This is what an AI neural network, a deep learning network, tries to simulate. So what we have over here is the set of inputs. Okay, just a basic introduction to neural networks, if those for those who are not used to it. So we have the input layer, which we pass in numerical data, right? Because computers work with numbers, and this entire thing, in fact, all of this mathematically representing it, it would just give you a bunch of matrix multiplications. Okay, so we deal with vectors a lot, we deal with matrix multiplications a lot. But for now, just keep imagining this in your mind. That we, whatever data input that we get, we somehow convert it to numbers. Okay, so for example, remember I told you about tokens in a sentence. So let's say we take a sentence, we break it down, and all those tokens, right? Let's say the word hello. Let's say I map hello. Okay, let's say a sentence. My name is Noel. So let's say I map it as one. Name, let's say map it as two. Is three, and Noel four. If I say 1, 2, 3, 4 to you, obviously it doesn't make any sense. However, I can train AI machine learning model to map AI 1, 2, 3, 4 to okay, or in other words, map my name is Noel to 1, 2, 3, 4, right? So I can convert text to numbers. I can do all the math and all the fancy stuff in between, and then I can get a set of numbers at the end, which I can then decode back into words, and I can show you the words. That's what ChatGPT is doing under the hood, right? Obviously, way more complicated. I simplified it a lot. However, this is how any neural network works. So you have a set of inputs, then you can see all these lines connecting them, right? They are something called as weights. Okay, so be multiplied by a weight. So let's say I have some value, and let's say this weight is less. Let's say let's say it's zero point 0.5, and this one is a bit more, 1.5. Okay, the weights random. It learns it through its training process. Okay, I've heard about training an AI model. So this is what we mean. Basically, all these are weights, and there are biases, right? So once we multiply all of it, we'll take a set of inputs. We will multiply every input with a certain value, which is our weights. So let's say W. So we have X as our input. We multiply it. Okay, let's say X is a matrix, right? It's an easy. Okay, we'll focus on one input. Okay, for now, to simplify things. So I take this, I multiply it by W1, W2, W3, W4, and W5, because there are 5 input layers, right? So over here, I'll multiply X by W1, W2, W3, and here the value stored is now W1X, right? And here to be W2X, W3X. All that stuff, I'll keep, what do you say? I'll have a set of numbers. And now there's something called a bias. So a bias is what you add or subtract. So right now I have multiplied it by some value, and now I'm going to add or subtract some values, which will determine the activation of a certain neuron. So the activation of a neuron uh, determines separate things, because, for example, in your brain, right, your brains need to send a decent enough of a strong signal to activate a certain neuron for it to give a signal to the other neuron. Okay, so if it doesn't reach that activation level, it will not send a signal, and it will say that, okay, for example, when I see this bottle, right, when I see the bottle again, it says pink, but the neurons for brown, right, when I give the when it gets a signal for brown, right, let's say one of these has like maybe how dark the color is, right? So if this neuron says that it's very bright or something like that, this neuron says it's very dark, right? So obviously brown is slightly more of a darker color. So this will have a high activation, and have a low activation, right? And it all depends on these weights and biases, right? And the bias will basically make sure that, okay, it's positive or negative. It basically gives you a score, right? So think of these as scores. Now we do this again and again and again till at the end we get our outputs. How do we get these weights? Through the training process. How do we get the biases? Through the training process. How do we train a machine learning model? I'll go through it a bit later. But right now, what I want you to imagine is, if I write this in mathematical notation, what I'm basically creating here, as in this entire neural network, is a function that takes in some input. It does a lot of math. It does a huge amount of math, a huge amount of computation, and it gives you some output. Right. So the output is probably the correct answer that I'm looking for. Right. That is what we're creating here. And why this huge amount of computation? We are basically creating a function to do whatever we want. So, for example, when we talk about ChatGPT, it's actually a mathematical function that once we give it a set of words, it answers our question or answers our query in the appropriate manner that we have trained it in. Right. So, imagine I have a math function that I give it a set of words, and it's able to give me a set of answers back. Right. So that's why obviously it's not easy to go from here to there. There are so many steps involved, right? It's unimaginable that math can do these sort of things. That's why these models are so huge, right? As in they work on billions of different parameters. So imagine I have a math formula with 8 billion different terms, right? And they are adding, subtracting, multiplying it in very complex ways. And this is what simulates learning, or it simulates intelligence for us, right? Our brain does the same thing, and what we work with neural networks, it's a way for us to represent that through code, right? Computer code. So yeah, this is our neural network. So basically, when we go forward, we there are two different types of training that you can have, pretty much. So one is supervised. So I will give it a set of inputs. I'll get a set of outputs. I'll get an answer. And once I get the answer, I will check, okay, is my answer right or wrong? So let's say I wanted this neuron. Let's say this neuron represents something. Okay, let's say it represents, okay, see, let's say the question is 2 plus 2. Okay, you will not, obviously, you don't need a neural network to solve 2 plus 2. However, it's a simple example, so we can go along with that. You can definitely have it. It's not impossible, but it's stupid to do so. But yeah, 2 plus 2. So let's say I encode it in some way and I pass it into all the parameters. And let's say the answers are 1, 2, 3, 4. Right. So obviously I want the final one, 4, to light up. Okay. Initially, right, when I give the question, when I just created the model and I'm trying to use it, it will set a random value to the weights and biases, right? So now the random value, obviously, it will give me gibberish behind it because there is no knowledge baked into the model. It's just a random set of values. So it will give me, and somewhat of a semi-equivalent distribution. It will activate one of them more than the other, and it might give me the answer is 2. So it will say 2 plus 2 is 2, which is wrong. And since I know the answer is 4, I can tell the model that no, the answer is wrong. It's 4. Okay. And remember, this is a mathematical formula, right? There are so many different parameters that you have. So you have X, you have Y, you have Z, you have billions of different, you could say, billions of different variables. So imagine a space, right? So if you have a two-dimensional, if you have, let's say, a function that has two variables, right? You can represent it as a plane, right? The xy plane. If you have three variables, you can represent it in the three-dimensional plane. If you have four, okay, it's very hard to represent it, right? Obviously. But however, we can imagine it as a four-dimensional plane because math doesn't care that whether we can imagine it or not, it will still work, right? Forget four, these AI machine learning models work on millions, if not billions, and modern large networks can work on trillions of different trillions of dimensions, right? It's impossible for us to imagine it or maybe simplify it in such a way that we can even visualize it. It's impossible. However, math still works, right? So right now, imagine there is a score that I give the model, right? So how accurate it is. So let's say that score is a function in this plane. I want to find the minimum of that function, right? So the gradient will give me the greatest ascent. So there's some. So if I take the negative of the gradient, it will go down, right? So I can go and try and find the minimum. If you want to look more into this, I'm going a bit quickly because this is a very large topic to go about it properly. However, basically, we're trying to find the minima of a function, of a very large function, and that's what gradient descent does. Okay, yeah. A YouTube page where you can look into all of this through greater depth is 3 Blue 1 Brown. Amazing channel, explains it so well and explains you the math so you can see what's actually going on at a fundamental level. For the code, again, different YouTube pages show different things. You can, I'll suggest some for our topics right now. But yeah, so we're trying to find the descent, right? In fact, there is one of the most important algorithms used for this is backpropagation, and that there's a video that explains backpropagation to you if you want to watch it on YouTube. That goes on for like around 5 to 6 hours. Okay, so these are very large topics. I'll skim over it for now. So yeah, this is how a neural network works. Okay, so let's start. Okay, so this is a neural network. There are different types of neural networks. Recurrent neural networks, we call it RNNs, CNNs, that are convolutional neural networks. Those are used for image tasks, you could say. RNNs used to be what we use for uh, natural language processing, right? So that's before ChatGPT. ChatGPT works on, let's say, a transformer architecture. Before transformers, we had RNNs and LSTMs, right? So LSTMs stand for long short-term memory. So both of them had their own issues. One of the issues with RNNs is that they are very serialized. So basically, RNNs, what you do is you take the output, you feed it back into this thing, right? Into the along. Let's say you have one input. So let's say that's one word. You pass it to the network, you get an output, you feed it into the network along with your new input. So now it will create with the next word, keeping the previous word in mind. Right. So you'll keep doing this again and again so it can create your sequence. In fact, the if you take your phone, right, and then you type out something and then you click on the center button to predict the next word, that is an RNN network. Okay, so if you do that a lot, I'm sure none of you have gotten any sort of a good sentence out of it. And that is shows you like how flawed RNNs are. Good for some things, bad for some other things, and but certainly not great for our purposes. But RNNs are simple. So this is how everything started, right? So RNNs are a specific AM architecture that you can use for that. However, we'll be looking to transformers, right? That is the modernized version. And basically, a transformer, defined in the attention is all you need paper, is an AI architecture that is exceptionally good at understanding context. Okay, so if I give you this paper, okay, when you read it, if I if I give you a sentence, right, like something with like a home of like okay, so the boat sails through the ocean, or the cloth is on or the dress is on sale right now, right? Sale means very different things between in these two sentences, right? So different words in depending on the context can have different meanings, right? Obviously. I so yeah, so his eyes were bloodshot. Okay, he might just be extremely angry. Odds are that his eyes weren't actually shot with blood. But again, these sort of very simple models will end up thinking like that, right? However, transformers don't do that. They understand the context behind certain text. So when you give it, let's say Michael Jordan is, right? We all know Michael Jordan is a great basketball player. I don't know, something. Okay, it'll say something that is probably not connected to Michael Jordan at all. However, the transformer will be like, oh, Michael Jordan is. It thinks, okay, Michael Jordan, the basketball player, probably is, and then it will try and predict the next word. So it'll be good. And now, again, we pass it to the model, right? Michael Jordan is good, and then it will probably predict the next word will be at. Then again, pass it to the model. Michael Jordan is good at basketball, right? So when we ask it questions like these, it produces the words one after the other, right? If you open up ChatGPT, right? When we use ChatGPT, any sort of a question. Hi, hello, how are you? Right. You can see it generate the response. You can see it generate the response one after the other. Right. So all these words, it generates tokens one after the other, depending on the tokens that are produced before it. Right. So this is what the transformer architecture is actually about. Okay. So now stay with me. It's a lot of really technical stuff. It's hard to follow along, I know, but if you want to implement it, I have mentioned links in the notes. If you want to watch videos that explain it, I have linked stuff in the notes as well. But I'll try my best to explain it. So once you go to those videos, you'll maybe figure out, oh, this is what he meant. Maybe this is what the other thing meant, right? So I hope to give you an overview that works really well for me, right? So this is the transformer architecture, the one that you see, that powers transformers as we know it. But yeah, this is an older paper, 2017, and as most of you know, Transformers. This was introduced back in 2017, and billions of dollars worth of research has been dumped into this field, AI, as we have all been using this. Like for example, Nvidia said recently, AI that they have powered, so they're powered by Nvidia. So AI is usually run on GPUs. I'll explain as to why later. But yeah, AI assists in about $100 trillion worth of businesses, and that's I believe pretty much the entire world economy. So yeah, there has been a huge amount of research that has gone into this to optimize this because so many people use this, and this is very computationally expensive. For example, the simple ChatGPT prompt that I sent right now has probably computed a couple billion different values just to give me that prompt. And couple billion as in like high billions, if not in the trillions of values, just to give me that one answer. Right. So these things have to be cheap for people to use them. Right. And they need to be fast because if it went from a trillion to maybe let's say a couple quadrillion calculations, you would never be able to get an answer. Right. So these are optimized. However, we will look at the transformer architecture because it's a simple one, and this is what we have the most info about. And pretty much everything else is a derivation of this. If you go into this rabbit hole, you will find infinite amounts of knowledge. But for now, we just start. And the start is extremely hard. So again, try and stay with me. I hope that you stay interested. But yeah, so now we have our word, right? So now the idea is I give ChatGPT a word, right? ChatGPT, Gemini, any sort of an LLM, right? Transformer, any sort of an input. So I take my let's say sentence, or let's say I take my image. So for image processing task, so let's say okay, anything. If I give it a sequence of tokens, right, some sort of an input, what I wanted. Okay, so first it will go through the encoder. Okay, yes, modern architectures do not have the encoder, they are only a decoder architecture. However, we'll go to the original one. So we have something called an encoder, right? So an encoder's basic job, we'll go about it over like an overview, and then we can go a bit into detail maybe later. But yeah, so basically what the encoder does is it takes your set of tokens, your input values, what like however you represent your data, it takes in that input, it processes it, and hopefully the idea is it's able to give you your output as a proper vector. Okay, so let's say I have this very okay, in a very proper like digestible manner, right? So it's able to encode meaning into those numbers, right? Proper meaning, like as in let's say my name is Noel. Okay, so imagine every possible question that you can ask about it. Okay, related and not related. Okay, is is the question describing an object? No. Is the question describing a person? Yes. Does the question contain a name? Yes. So for every single possible question, for all those millions of questions that you can possibly ask, it hopefully gives you an answer that encodes yes or no for all those possible questions, right? So it basically gives you a matrix for, and where every single column is your word. Every column represents a word, and that matrix, that massive matrix that you have, massive as in like these are in the tens of thousands of dimensions. So these matrices that you have, they encode values, yes or no answers, pretty much for pretty much every question that you can ask, right? So yeah, so you have your input embedding, and now you pass it into your decoder part of the transformer. Okay, so there's something called self-attention. So self-attention is basically the part of this transformer that makes it special, right? There's nothing too special about the entire architecture, the rest of it. So yeah, I told you about parameters, right? So when I talk about neural networks, right, all these values, all these weights, and all these biases are things we call parameters, because parameters are things that you can change, right? So if I want my answer to be something else, I can. So imagine these are all like dials that I can turn. That if I maybe turn this here or turn that like this, if I change all these numeric values, maybe my answer will end up going to the correct answer, right? Not to something else, diverge completely into something else, nonsense. So basically, parameters is how you measure the size of a model, right? If you have many parameters, that means there are lots more calculations that you have to go through. And when you talk about model size, this size will be bigger as well, because more parameters means a larger model size. So if I want to send you over the model, so for example, when we went to Hugging Face, right, we saw the 70 billion parameter model. So yeah, let's say the, okay, again, llama. Yeah. So if I talk about this one, right, you can see 70B. 70B is the size of the model. So 70 billion parameter model, right? So this model has 70 billion parameters, right? So it has 70 billion of these connections and those weights and biases that it uses to give you your answer. Okay. But there are other models that are maybe 1 billion parameters, couple hundred million parameters, maybe others that are in the trillions of parameters, right? So these are genuinely, so there's a huge variance between these. So yeah, about a third of the parameters lie in the attention blocks, we call it the self-attention or multi-headed attention blocks. So okay, I'll explain what they are later, but about a third of the parameters lie in the attention blocks, and the two-thirds of the parameters lie in the feed-forward network. The feed-forward network is pretty much the old school machine, like, neural network. However, this is something special, and this is where the magic happens, right? So I mentioned about the contextual meaning. So all these things, so when I talk about context, right, so something that I said early on affects something that I say later, right? Context matters. So self-attention is basically what encodes that context, right? So when I say something to ChatGPT remembers so much and then gives you an answer that is specific to your context, right? So self-attention is the attention blocks, and then your feed-forward network. See, the thing with neural networks, okay, is that you will never know exactly what's going on. Okay, in fact, with the embedding model, yes, we can test it out, and thank God that works in a proper manner. I'll tell you how it works. The parameters, we understand what they're doing properly. However, here, when we go deeper into the neural network, it's like a black box, right? We can figure out and we can hope that it works like this, but there's no real way to understand that, yes, I know for sure this specific part does these stuff, right? I'm telling you that as reality. However, for our purposes to learn these models and how to create them in the future if you want to, or like how to use them, or just to get an understanding of these models, it is very helpful to think of them as doing certain stuff, right? So the attention blocks, we know what they're doing. They're encoding contextual meaning into the, you could say, the words that we have given it, right? It is encoding context within that word. And now in the feed forward network, this we do not know what it's actually doing. However, we can hope, and what we guess it's doing is, maybe you could say, storing information, right? Because Michael Jordan is a tall man, he is in the US, whatever, whatever. All that context is there. However, nothing that I have said hints to that he's a basketball player, right? However, the model, through the entire training process, it has seen all of the internet's knowledge. So it goes like, it remembers from its training that, oh, Michael Jordan, the one that he's talking about, is also that famous basketball player. And the text that he has provided, it seems like he's talking about that basketball player. So that data is somehow stored over here. And that is now encoded into the text as it moves through this network. Okay, so we give it a certain amount of text, it manipulates all that text, it manipulates it even more, it gives context to different layers, it changes all those values a lot, and now over here it adds more values and it manipulates other values to encode memory as well. Okay, and now So it's a lot of math. The text that we have given, it manipulates that a lot, and now we reach this final state. And this final state, what? Okay, this softmax function is pretty much nothing. It basically gives you a probability score. So let's say it gives you a lot of values of what. Okay, so let's say every single word that you can imagine, right? For example, this model, let's say ChatGPT 3. Okay, this is an open source model. It had about 175 billion parameters and a lot of and this was released long back. It was basically used to complete text. So let's say I gave it this text, it was able to generate words later after this, after the text given, right? So it is able to like complete paragraphs. So if I give it an input paragraph, it was able to continue the text for me, right? It's not like the ChatGPT that we know now, okay, or Gemini that we know now. It was able to complete the text for us, right? So it's able to predict the next step. So basically, what the softmax function. Okay, so imagine it has a vocabulary of about 50,000 words. It gives you a probability score of which word could possibly come next. So words that make no sense. Okay, so for example, my name is, let's say, a fridge. Okay, fridge would make zero sense in that context, right? So fridge would have a very low probability score, and let's say some name, let's say Michael or Andrew or Leo or whatever it may be, has somewhat of a higher score, right? So whatever the model thinks has the highest score, it will give it a probability. So depending on the probabilities, it will be like, oh, okay, this name has a high probability, put that name there. Okay, I will put that name there for you. Okay, so that's basically what the softmax function does. It takes in a set of values, it converts them into probability scores. So values that are between 0 and 1 and that add up to 1, right? That's a probability distribution, right? So it gives you all of that and gives you your output, right? So now, if you want, okay, so that's pretty much what you can go. So as I said, tokenization, it will be able to split it into words. And then you have your embedding layer. Your embedding layer is your where we convert our text to your what do you say, your vector. Okay, so now I will start using the word vector. So vector is pretty much, again, a set of values in a list, right? Whatever you want to say. Or the how we describe it in math or physics, it's basically the vectors are related to directions, right? Or when we have this hyperdimensional space, a vector points to a certain spot in that dimension, right? So let's say I have this. So imagine to yourself that there is this dimension, okay, like this graph with billions of different, like, okay, not, it's like, let's say millions of billions of different ways of question that you can ask, right? So let's say one direction encodes heat. Okay, so let's say I have cookie. Okay, cookie points in this direction. Let's say I have another vector for hot. Okay, so now if I add it to this vector, what should I get as my output? Hot cookie, right? Or something along those lines, right? This is what actually happens with the embedding layer, right? So we start off with random values. However, throughout this entire hyperdimensional space, it is able to convert all these tokens into new embeddings or vectors, where the word, right, vector representing the word is related to some sort of a direction in that hyperdimensional space. So let's say we have a vector, and so in fact this is very useful for different things, because right now we have this like, imagine this graph that you have, where every point that you have represents a very specific word, and there are directions that you can go that encodes different meaning, right? So let's say I have cookie, and if I go in the direction of cookie, if I go in the direction of heat from cookie, I'll end up at hot cookie. Or else if I go in the direction of uncle, and if I go in the direction of, let's say, female, right, I'll get aunt, right? So now remember, we can have, okay, so now this is a very useful thing. In fact, this part alone is used for so many different things, because right now we are encoding meaning, right? So if we want to search for things through meaning alone, this thing comes into play. I'll explain as to how later, but yeah, that's what we can do, right? So yeah, that's the embedding layer. So you have your position encoding, as I said, the encoder and all that stuff. Not too important. And yeah, right now we have the self-attention blocks, right? Self-attention is extremely, it's a complicated topic. Okay, I do not think I should. Okay, so basically, when we talk about attention, basically, okay, so I won't go too much into the details because it'll start getting boring. It goes too much into math. And again, as I said, Three Blue, One Brown has an amazing series on this. Watch him. He has amazing animations for all of it. So you can follow along with your eyes. I'm sorry, I do not have it as of right now. I cannot do it myself. But yeah. Okay, so we have self-attention. There's a thing called the key, query, key, and value vectors. So I will not go into it in detail. I think that's best, honestly. However, just understand that your key, your query, key, and value vectors are basically a bunch of questions that you can ask about your word, right? So when we give it a sentence, so it asks a bunch of questions. Okay, it's an imagination. All the values are determined by whatever optimal path the machine learning model or the training program takes. However, let's imagine right now that is asking a question to your sentence. Okay, so let's say the query vector is asking, are you a noun, right? So for each word in the sentence, okay, it will say, okay, so my name is Noel, right? So all those words, it'll ask, my, is it a noun? No. Name, is it a noun? No. Is, no. Noel, yes, it found a noun. So now it's the same. Is it preceded by a noun? It'll do the same thing. Or like like pretty much any different question that you can ask, okay? It'll ask a shit, like an insane number of questions from that text that you provided it. And basically, you have your query, you have your key vector, both are determined by the model. It'll do a dot product of both of them, and then there'll be a softmax function, your v, it'll multiply it by your v, divided by your dimensionality in the space. Okay, basically, it'll do some mathematical operations on your query, key, and value vectors, and it will normalize them. And basically, what it does is your input text, right? So right now it has gone through the embedding layer. So now it has been mapped to whatever embeddings the model finds appropriate. Like, let's say different values that encode different meaning, right? So right now all these vectors have meaning that you have given it. Now your self-attention block basically asks a lot of questions, and because now it has its meaning stored as numbers, it's able to take those numbers, ask it a bunch of questions, and it's able to basically get info out of it, take that info and get your value vectors, right? So your value vector is basically what should be added to that next text. That uh, basically it gives you the so the value vector that is added to your new, like, current text, right? It basically converts that text into a new vector that is basically useful, that somehow encodes the context with the thing, right? So that is what we call a self-attention head, right? That's a singular head of attention. So when we okay, so right now ChatGPT 3, when we look at the model parameter counts or whatever, it has like around 96 heads running in parallel. So imagine it asks so many questions, right? And it encodes contextual meaning to each one of them. All those attention blocks, right? Like each one is called an attention block or a head of attention. So each one of those attention blocks run in parallel, right? So 96 of them run in parallel, and this is where this is what we call multi-headed attention, right? So each one of them can maybe encode a different type of information into into the text that you have provided it, right? So so again, from the top, we give some text, it converts those texts into numbers that have meaning behind it. All those numbers point to vectors that encode the meaning of those words in a hyperdimensional space. Now we go forward again through the self-attention blocks, and the self-attention blocks, depending on the words around it. Okay, so let's say all the words, if I give it a sentence, right? All the words around it. So Michael Jordan is a basketball player, and okay, so all this context around it, right? It's able to encode this new matrix, the text that you've given it. It's able to change all those values so that now those new values also have the contextual meaning between those words, right? And okay, one block will encode some context, some sort of context. It have a set number of questions, let's say. Now this block will have another set. Okay, it will encode different context. All like that. We have 96 different heads, right? 96 heads running in parallel, that I said. Now it goes through another 96 layers. So we have all this running in parallel, 96. in parallel. Now all of that will be linked to its own set of different self-attention heads, and those will be linked to another set of self-attention heads 96 times, right? So when we talk about 175 billion parameters, right? So ChatGPT 3, it has 175 billion parameters, right? We'll break all of them down into its how all these parameters are stored. So all these parameters are stored in 27,938 different matrices. All those matrices are now separated in different parts of the model, right? So now your embedding value. So when you have your embedding thing, right? So basically, when you give it text, your vocabulary size in ChatGPT 3. Okay, its vocabulary size is 50,257, and its embedding size dimensionality is 12,288. Your 50,257 is your vocabulary for your LLM model, right? So your vocabulary is all the words that the model knows, right? So each column is a number that they found convenient, right? So right now 50,000 possibilities of words, and the 12,288 is the dimensions in which it can exist, right? So over here, when we multiply these, let's say you have a matrix, when you divide them, matrix 50,000 by 12,000, you would have these many number of values in that one matrix, right? So this is your embedding matrix. This is your text that is passed through. Okay, so after you have your text, it goes through your attention block. Okay, so your attention block, as we said, contains your key, your query, your value. It does some math between them, and now all that math is okay. So your key and your okay, so as I said, 12,288 is the same, because again it has to match the dimensionality. We know about how matrix multiplication works, and now this 128 is basically, it's less than 50,257. If it was 50,257, the output matrix would be the same as the input matrix, the dimensionality I'm saying. However, since we have it as 128, it's now scaled down. It goes down from this hyperdimensional space to these new set of dimensions, right? So it's scaled down for efficiency's sake, obviously. Okay, so now it's scaled down, right? Now it does some more math between itself with the key, the query, and the value. And now all of this represents one block of attention. And one block of attention runs with 95 others, so 96 total attention blocks in parallel. And all these blocks are now layered on top of each other like a cake. That is 96 tall, right? So each block would represent around 1.5 billion parameters. And into 96, okay, 1.5 million parameters, my bad, multiplied by 96 for parallel, 96 in depth, that will add up to 14 billion parameters for both your key, your query, and your value vectors, right? Now your output, okay, your output is again, that is towards the very end. Okay, again, output from the key query, this thing, right? So from all of your different attention blocks, taken all the outputs and give you one singular output at the end, as we saw in the architecture. So there'll be, this represents so many different, right? So you have so many different values going in, so many different values going out. So your normalization functions, again, those are like machine learning terms. When you work with these neural networks, these are basically functions that help normalize values. What normalization is, uh, again, if you work with neural networks, but yeah, so let's go back. So yeah, so right now your output is from the attention blocks. So I told you this part is about 1/3 of the total number of parameters. This is where your 2/3 of the parameter lies, your up projection and down projection. Up projection, down projection, detail what up projection is. Down projection, we are basically scaling up the dimensionality, doing work over there, and scaling down the dimensionality again at the very end to give us a value at the end. Okay, why we are scaling up the dimensionality? It works. Okay, so this is our traditional MLP, or MLP, multi-level perceptron. Very cool name, that's why I mentioned it. But yeah, it's basically a neural network. This one is pretty much this, but side by side, right? So imagine for every single column in that vector. So as I said, remember we had the output vector. The output vector would have a dimensionality of, let's say, this much. It will take all of that, it will scale it up, and every single row will represent one word, right? As I told you in the beginning. So every word will now pass through this network. So like imagine this as one layer of the MLP, right? So every word will pass through this network, and at each layer, we take the output, we add it to the original vector, and we pass it forward. So basically, we're adding info. Okay, so we'll ask some question, we'll add info, we will encode info into that input text. I tell you, the deeper we go into the network, the less we know what actually goes on. Right now, we are imagining what it does, right? So maybe trying to think of how they came up with this architecture, right? So yeah, this is what we hope that it does. And through experimentation, we know this is not what it actually does, but it is useful to think of it this way. Again, when you train your own neural networks that are completely from scratch, or when you are a researcher in this field, it's useful to think about things in these ways, right? So now the entire, so each word is now passed through this network, it's added to it. So now the old vector is added to the new output vector, and it's moved forward because this old vector is added to the new vector, and it has meaning encoded into that vector, right? The vector is the word, right? So now let's say your words have some other meaning attached to it, right? So that represents some more data, right? It keeps going forward. Okay, all these words in parallel, it will keep going forward one by one by one, and it will go through an extremely large number of calculations. If you add both of these, they are like about 115, almost 116 billion parameters right here. So 2/3 of the parameters that you have are just in this, just in this, just to encode memories, or like say memories of the model, or else data or knowledge that we have here, right? Or knowledge that it has learned through its, what do you say? Knowledge that it has learned through its training process. So once it passes through this, the final vector that we have, right? Now we basically use all of this data to predict the next vector in that sequence, right? It all of this math is done so that we can get a probability score for the next set of values that can possibly okay, let's say there's a final vector which is like 50,000 dimensions. Okay, so yeah, you have 50,000 dimensions over here. So it'll give you a probability distribution among all those words, right? So it'll give you like a probability that, okay, the next word can be this or that or this or that. Some will be highly unlikely, some will be moderately likely, some will be highly likely, right? So it'll choose maybe the most likely, or like if you want some creativity, you might not always want the most likely because it'll just give you very plain text. If you want the model to be somewhat creative, you can ask it to be choose maybe the second or your third most likely ones, and can choose those and it can give it to you. However, that's not ideal. It's okay, it's a mix and match situation, because sometimes it can be too creative and might give you nonsense, right? So you don't want that. So it'll give you a vector at the very end that encodes the next token, right? So once we have that, our input text plus one extra token. Right now what we did was to generate one single token, right? So we went through all this math, got one token out. Now that one token is our new word. This unembedding vector, unembedding matrix that we have is now a way to scale this new vector that we have at the end down. Okay, I mean we have a bunch of vectors right now, right? So here we have the embedding vector where we take our input text and we convert them to words. This is basically the opposite. We're taking the words and we're converting back into text. That's it. Okay, so now we have created one singular token. So I don't know if you remember from what we saw in ChatGPT. One second, let's say ChatGPT. Yeah. Um, can you give me some info on transformers in AI? So right now, you can see every single token that is generating one by one, right? All those tokens are being generated by this entire massive process, right? So this is what I meant by it does billions of calculations to give you that one singular token. And it does it on and on and on till you get your answer. Now, what I told you is basically giving you an answer that is most apt for the continuation of that sequence, right? So let's say you have some words. Right now, you're trying to continue from that sequence, right? You're trying to predict the next word and the word after that and the word after that. That's not what I use these LLMs for. right? For example, when I ask ChatGPT, can you give me some information on AI? What it will do by default, the LLM by default, what it does is it will extend that question. So it will ask, can you give me some info on transformers in AI and ML and blah 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 blah. It will basically make my question into a much bigger question, which is useful for some tasks, very useless for most tasks. So right now what we have done is the unsupervised version of training the model. So right now I've given the model a huge amount of text, asked it to predict word after word all those texts, like basically learn that entire text and be able to predict the next word in a sequence, right? Given contextual info, right? Keeping in mind contextual info, it's able to predict the next word. Now, what I do is I I switch from unsupervised to supervised learning. So, whereas let's say the question, right? All these questions are actually, I give it a question. However, on OpenAI side, what they take is they take your question, they split it into, they cover it in these things called question tokens. So, let's say there's some token that represents a question. So, when the LLM sees that, it'll be like, oh my God, this is a question, right? And it'll be like, okay, once it sees the question, it goes like, okay, that's the question. What is the most appropriate way of answering it, right? So there are these data sets that you can get that represent all this. So for example, this is a data set that does that certain thing. So let's say that represents this fine-tuning process, right? So as I said, you have your LLM that's able to predict the next token. That is unsupervised learning. That is trained through unsupervised learning. And when we have the supervised learning part, we pass it. We call it fine tuning. So we take this model that we have just trained, right? And now we tweak all the values again, but not fully. What we do is that, okay, we basically train the model to go like, okay, if I ask you a question, I don't want you to extend the question, I want you to answer appropriately, right? So now it's able to it now, after the fine tuning process, whatever purpose we have, it'll be able to do all of that properly. So yeah, so so it's able to answer your questions. My apologies. So yeah, it's able to answer your question. So now we are done with the transformer architecture. I'm pretty sure a lot of it is way too much as of right now. If you understood well, amazing. If not, you can go through the notes. There are lots of notes over here. I've tried to add as much as I can. There are plenty of sources that are cited. There are YouTube videos that I have linked as well. I have forgotten to link Three Blue One Brown's YouTube page as well. Amazing page. I cannot say enough. Just for math in general, but even about AI or machine learning, if you want to learn more, Three Blue One Brown is certainly amazing for that. So you can learn through there as well. But yeah, the notes are available to you. Try to make use of it, and other resources as well if you do not understand and if you want to go into more depth, right? So now we go into the fun part, right? Because all of this is extremely large. If you want to train a model, like I told you, this one is 175 billion parameters, right? It's a pretty large model, but this is old, very old, right? ChatGPT 3. We have mostly played with ChatGPT 3.5. After that, we got ChatGPT 4, ChatGPT 4.0, Turbo, and right now we're going into ChatGPT 0.1. We have the Gemini models and their series, and there's so many different models that we have gone. Many of them are absurdly large. In fact, right now, you can go, okay, let's say Llama 405. Yeah, so this model that I can download right now onto my laptop, okay, this model, look at its name, 405 billion parameters, right? That is way more than ChatGPT 3.5, ChatGPT 3. Okay, just some quick math, a simple way. Okay, all these values are numbers, right? So let's say all of them are 32-bit floating point integers, which is like a 4-byte number. A 4-byte number into 175 billion it means you would require around 700 gigabytes of RAM to run it, and not just any normal RAM. You would require 750 gigabytes of VRAM, that is the RAM attached to your GPU, which is way more expensive because if you have to use GPU compute, you have to use it on VRAM, right? 750 GBs of VRAM, okay, just for this one model. Or else, let's say I talk about like Llama 405 billion parameters, right? That again multiplied by 4, that'll be what, 1.8 terabytes over that, in fact, which is an absolute mental amount of VRAM. And that is just to load in the model. As in, let's say I take that model, if I press run code, I do not ask anything. I do not ask a single question. I just load in the model. It will take up 1.8 terabytes of RAM. Okay. If I ask it a question, it will double. So it takes an insane amount of computational resources to use the model. And using the model is, in fact, the tiny part. In fact, the using the model is such a small thing. Training the model is absolutely absurdly computationally expensive. In fact, okay, for example, 405 billion parameters. Okay, Llama, that is Facebook's Facebook's AI models. They have released a research paper on this as well. One second, I believe it's here. Just give me a second. I'll try to find it. But uh, oh yeah, also in the in the notes for all this, I have also typed out some code. Okay, again, all this code is basically your transformer architecture from scratch. Okay, so Torch is basically this library that you can use that does like vector multiplication on your GPU. It's basically it's used for machine learning pretty much. So from that, this code, if you run it, it's basically your transformer architecture running on your laptop, right? You're trying to create your model. However, this is the architecture in one code. However, there's a lot of other files. For example, the data set you have to train it would be, for example, the one mentioned in the video that I use as reference would be around 45 gigabytes. Obviously, I can't send it to you as notes right now through that. So this is just the code. If you want to actually use it, either watch Andrew Karpathy. He's one of the founding members of OpenAI. And the other one is Freecode Camp has another amazing video as well. It's a 5.5 hour long video about this. Amazing videos, very informative. You understand what's going on at such a low level. But then this is just that, just for curiosity's sake that I mentioned this. But if you want to build it yourself, it's over there. But yeah. So I have mentioned your Llama paper, right? Where is it? So yeah, so this is like as I said, this is the transformer architecture mentioned in your attention is all you need paper. Your Llama model is something that's like this, right? So the Llama model is not as small as the other one. Oh my bad, the link that I don't know that this is a temporary link. Okay, just look up the paper yourself. Basically, the paper is like 92 pages long, and it describes to you the exact problems that they face training this large of a model and how they did it. It's in extreme depth, right? So training a model, as you scale up, a whole huge amount of issues that you will not even imagine start coming up out of nowhere, right? So your model size cannot run on one GPU anymore. Even if you have hundreds of thousands of dollars worth of GPUs, you cannot run one instance of that model. You cannot do many different things, right? Training the model, overfitting, how much time it takes, it's very expensive as well. For example, this model itself is worth like maybe millions of dollars just to train the model, right? In fact, even your 8 billion parameter model, that would take maybe $250,000 in resources just to train that one model, right? So obviously we cannot train these models easily. However, we can use them, right? Because many companies, for example, Llama, have been kind enough to open source these models and give us the model weights. And we don't require anything else. We don't require to train anything. We can just use the model weights to do whatever we want, right? So again, I've mentioned over here how we can either call an API. So I can send a request. So I can ask Google. I can ask the Gemini through their Gemini API. I've given some steps over here. Okay, I can say that, hello, I am, let's say, Noel. So Noel has a certain API key. So that's like my password. So I'll say, I am Noel. I want you to answer this question. And I can give it my question and it'll give me an answer and then I can use it back. Okay. It's very simple, very cool. I can just mention the model that I want to use over here and it works by itself. Or else another way is you can, for example, from here, Hugging Face, Again, APIs are very simple to run. They do not require anything from your system. As long as your system has an internet connection, it's fine. However, from an industry standpoint, there, you have to start paying money and stuff. But however, there are plenty of free APIs. Gemini as well has a free API available that you can use for free, and that's really nice as well, that you can use. So the purpose of an API is that you can create code that uses all of this for different tasks, right? You can automate the process of using these LLMs, right? So you can use the Gemini API. You can use Grok. Grok runs these large language models on LPUs, that basically language processing units. You could say uh, Google has their TPUs, your tensor processing units. A vector in machine learning lingo is termed as a tensor, whereas you could say, yeah, over here we say okay. So a tensor processing unit is basically a GPU, so your graphical processing unit. Okay, so as I said, right, the reason why we run these things on GPUs, CPUs are very sequential. They're very good for like for a wide range of tasks, but then they're not that ideal for most cases, right? So they have a certain, like, they have a low core count. So let's say they have my laptop, right? It has an i9. It has 24 cores available. So I can parallelize it at most up to 24 times or to 32 threads, right? Through hyperthreading in Intel. If I have a GPU, right? My GPU is capable of running the computation, the matrix multiplication, 7,000 different times in parallel, 7,000 different parts in parallel, I can get the answer, right? So this is what they do on a large scale as well. So yeah, GPUs are sort of power hungry, and they are good for graphical processing. However, they're not optimized for tensor processing. So uh, Google has tensor processing unit for their AI/ML tasks. However, Grok has LPUs for the language processing units. So they run their models. They have designed their own chips, and they run their models on LPUs, which give extremely fast inference speeds. So if I ask it a question, it gives you the answer absurdly fast. So you can mention your models over there as well. It has a free API available. It's really good. So yeah, that is your Grok, right? You can use the ChatGPT API as well. Though I believe that it's paid. You can use Hugging Face. Many of the models are actually hosted. In fact, Mistral, right? Mistral 8P, for example. Let's say Mistral 8B or whatever. I can use it through. Oh, this is through NVIDIA. Okay, just I don't want to keep searching. It's a waste of time. However, you can use some models on Hugging Face through their API as well. Again, it's free. Or else, if you want to run it locally, let's say, I don't know, for whatever purpose you want to run it locally, just for fun's sake, for example, you can download the model weights. You can, in fact, what do we say? You can download the model weights onto your laptop. For example, through Hugging Face, they have modules and stuff. They have their own set of instructions, their documentation, everything that you would require. So, for example, you can go to Transformers, and then like you can get a character, as much info as you want. You can go search over here, and how to use their API is mentioned over here. You can download their models, and then you can use it through this as well, where you will use your computer's resources to run these models. But obviously, to run a model, do not choose something like a 70 billion parameter model. Remember, I told you about uh, the model parameter count, right? The To calculate how much RAM you need. So 70 billion parameters, you would require around 280 GBs of RAM. If I have an 8 billion parameter model, I would require around 32 GBs of VRAM, right? I do not have that. However, there are other ways to optimize it, right? So, for example, there's a thing called quantization. I don't think I mentioned quantization over here, but basically, instead of using 4 byte floating point integers, I can convert them into maybe, let's say, 4 bit, okay, floating point integers. Obviously, the accuracy of the model will decrease. However, there are ways to make it not by that much. It's super amazing. There's also something called Unsloth, and Unsloth is truly magical. In fact, Unsloth optimizes it to such a point that yeah, so Unsloth, you can fine tune your models, you can run these models absurdly fast. In fact, they brag about it. So like they brag about it on their page. But using Unsloth, they optimize it so that you could say it runs extremely efficiently on a system as well. So if you have a weaker system, I would say, okay, use Unsloth as well. They go through their documentation. You can use Unsloth to run your models locally as well. So yeah, that is how to run them locally. After you start running these AI models locally, what can you do with it? Okay, I can ask it a question, I can get an answer back. Very fun, it's very interesting. However, I have ChatGPT, right? You can now build, but again, right now, since you have it in code, you can build systems with it, right? You can automate stuff with it. You can do lots of things with AI. So now, so for example, I have a bunch of stuff mentioned over here. So I named it optimizing LLMs. A better way of saying it is use cases of LLMs, different ways, methodologies that you can adopt to use these LLMs. So remember, I said, for example, RAG, right? Retrieval augmented generation. Uh, RAG is basically, I told you, you give it a set of an input sequence, right? It converts it into vectors, and those vectors have meaning to it. Let's say I give it a huge amount of text, let's say a document. I convert them to vectors. Now I take those vectors and I store it in some database. Okay, what sort of okay, it's mentioned over here, but in some sort of a database, I store it. Now, if I take a question, okay, if I convert that question to uh, let's say I convert that question to its embedding. If I take a dot product, okay, so remember all these are vectors, right? So if I take the dot product of my question vector with across all the vectors in my document, right? So my document is split into so many different vectors. If I take a dot product among all of them, the dot product that most that is closest to one, right? So where they are pointing towards the same direction, usually those ones are texts that have similar meaning to my question, right? That is, in other words, those uh, the answer to my question probably lies within the text in these documents, right? So RAG can is used for many different types of like it's used for many different things. That you can build huge systems on sort of on top of RAG. You can add your own info to the documents, and you can ask your LLM to respond with the context provided through RAG. Many different things. Look into RAG; it's very interesting. There are modules. Okay, there are modules that like Llama Index or like Llama Index, LangChain that make that you could say abstract away a lot of the deeper functionalities of RAG. I'm not going to the deeper functionalities, but yeah, this is basically what RAG does at a high level. So Llama Index takes care of most of it for you. So use Llama Index, use LangChain, they're very user friendly. Okay, and then you have prompt engineering. Obviously, I can ask a question in a good way. I can ask a question in a bad way. If I ask a question in a good way, I can get a good answer. If I ask a question in a bad way, I can get a bad answer. So the entire purpose of prompt engineering is being able to ask a question in the most optimal way that the LLM can respond in the best way possible, right? Then there's something called distillation. Okay, now this is again affecting your model. Distillation is mostly done by companies. In fact, I believe the Gemini model that you can use open source, like not open source, I mean the Gemini model that you can use for free is highly distilled. What distillation does is the process, no need to describe it. It's kind of complicated, it's kind of long, but in short, okay, text to image models, right? If you have played around with some of them, the Mid Journey, for example, Mid Journey, Stable Diffusion, any of them, what they do is they take a set of static. So let's say static. So let's say I have some random static like this. They take that static, they take my word, right, my prompt. Okay, let's say I want a picture of uh, a, I don't know, let's say a maize field, okay, or a rice field or whatever. To take the static with my prompt, okay, my text added to it, it will start refining the static to slowly change from static one after the other, step by step. So let's say it will take maybe around 16 steps. Okay, so 16 steps, it will convert from this to some other picture of a rice field, something like this, right? So it will go through that entire process, and hopefully it will give me some sort of, okay, its imagination of a rice field. However, through model distillation, you can greatly improve the performance. Instead of taking 16 steps to go from static to image, it can in fact do it in one step. In fact, if you take your phone, you go to Insta, and then you have that option to like create your own image, your imagine. When you type in word by word, right? When you type in one singular word, a generated image instantly pops up, right? so it'll give you a preview. So that is through model distillation, right? Because it'll take that away, the 16 steps away, it'll take it down to just one step, okay, or 0 steps. It just instantly produces your image from nothing, okay, from one set of static, okay. However, quality is greatly affected by distillation. Quantization also affects it, but however, sometimes the trade-offs are worth it, right? So that's one thing. Fine tuning, however, it's again like some issue. Okay, it's very good, it's very accurate. You can change the, for example, along with your models, you can see that this is an instruct model, right? An instruct model is you give it an instruction, it'll carry out that instruction for you. There are these base models as well. And I told you, right, when you train an LLM, it just predicts the next token in that sequence. So your base LLM does that. The instruct after fine tuning, you can change its purpose to do different tasks as well. So you have that. Memory augmented networks, for example, your like your ChatGPT, your chatbot part. As you talk, it is able to take text. It is able to have memory of your previous context and able to answer accordingly as well. That is your memory augmented thing. There's a table here for you. And again, use cases. This is very cool. So your AI agents. I will not go too deep into this, but this is probably like the future of AI right now, your AI agentic networks. So this is pretty much your Jarvis. You ask your AI to do something, and it'll call upon different LLMs to do different things. It'll call code that you have written down. It'll execute that. It's able to fetch data, whatever you have given it rights to do so. It's able to give a question and carry out many different tasks accordingly. Okay, so that's AI agentic works. So you give it a question, it'll keep doing more and more. It'll keep distributing the task to different people and different processes to carry out your process, and so that you're successful, right? Whatever question you ask, it'll make sure that it's done, right? That's what it tries to do. Chain of thought reasoning as well. So now let's say I asked a question, it directly gives you an answer, or else I give a question to the LLM and it's able to think before it answers, right? So it generates text, okay, and it uses that as context, right? So it'll think and it'll generate some stuff. It'll try to find flaws in its reasoning, all that stuff, blah blah blah. However, an LLM would do it. There are different ways of doing it. However, the chain of thought reasoning is as a person does it, right? So if you ask me a question, I'll be thinking, oh, this is correct, this is wrong, this is what I've known before, blah 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 blah. After all of that, it's able to think more and more and more, and at the very end, you get extremely high quality answers, right? So in fact, the best models that you can use right now, one of the best models that you can use right now is actually this Nemotron model. It's open source, trained by NVIDIA. It's a fine-tuned version of your Llama 3.1. Super amazing model. It's a NVLM, so it's a multimodal model. A multimodal model is pretty much a model that can take image input as well as textual input, different types of input as well, file formats. So yeah, uh, where was I? I was talking about chain of thought reasoning, right? The best models right now is pretty much your Nemotron model and then your ChatGPT 4.0, right? Again, you can use ChatGPT 4.0 a bit right now, but again, there's only a certain amount that you can use it before it starts limiting you, and then if you want higher limits, you have to pay, right? In fact, there's a way, if you implement this yourself with free APIs that are available, you can implement chain of thought reasoning and you're able to get incredibly good, like even better than 4.0 level of answers, okay? And it's able to give you such detailed, such beautiful answers, such amazingly high quality answers through just thinking more. Obviously, it thinks so much, so it takes time to produce your answer. However, that's it, okay? It takes time to produce an answer, but that's all that it does. Yeah. So now that's your chain of thought reasoning, right? In fact, you might have heard about ChatGPT o1. So ChatGPT o1 is basically your LLM that thinks before it answers, and that is by far the best AI model that has been released, LLM model that has been released, and its capabilities are truly astonishing. But I'm running short of time, so I will not go about that. But ChatGPT o1 uses chain of thought reasoning before it answers as well. So now we learned about the transformer model. We have learned about LLMs. About the transformer model, right? When I talk about transformers, it's used for being able to encode like contextual knowledge, right? So if I have a huge amount of context, it's able to look at the entire sequence and then able to give an answer that properly fits that sequence. Some of its purposes are language modeling tasks like this, translation, all that stuff. Anything related to language, it's useful here. Text to image is another one, transformer model. So you give it a text input, your sequence of static. It'll take the input, your text as the first input, convert it to some sort of an image. It'll start converting it and taking that as your context. Start converting more and more into your preferred prompt, right? Whatever your prompt asked it to do. However, another very popular task is your protein modeling, right? Your protein structure modeling. So, okay. So one thing with like as I wanted to do, I wanted to help people. I wanted to be a doctor or something growing up. But however, being a doctor takes a lot of time, and I did not want to do that, right? And I could not go through all that time. And it was a dream of mine to be like, if I'm a really good computer science engineer, I'll be able to create software that helps a lot of different people, right? Through whatever field. That's why this topic interested me so much, because like, okay, I did not go into the medical field. However, this is pretty much AI or computer science winning the Nobel Prize in chemistry for a biology problem, right? So this is what we'll be learning about. AlphaFold, we'll switch over the topic. AlphaFold is an AI protein structure prediction model, right? So why do we need to know the structure of proteins, right? So proteins, as we all know, they're very long, like molecules. And what happens is proteins are pretty much cellular machines, right? When we have proteins, uh, pro- protein machinery. Okay, proteins are basically called biological machines because, in fact, protein that looks like a motor. See, so for example, there are proteins, right? That do this. I'm pretty sure you guys have seen this video where it carries a molecule and it pretty much walks. Okay. There's another protein that looks exactly like a gearbox. Okay. So all these proteins are basically our cells building machines, right? That carry out a function. So just as a machine, its function is described by its structure. The same way, proteins have the same thing as well. Okay, so its function is encoded into its structure. However, these structures are extremely complicated to like to figure out, right? So before, through the older methods of getting these structures, what we used to do was we used to get a crystal of these proteins. We used to pass an electron beam through them. We used to get the electron densities, and then like we have to map all the amino acid sequences, and we have to get the amino acid sequence, and that's how we get, and then like the way the amino acid sequences like fold, and like a PhD student has to sit and like look at the electron density diagram, and then like map all of it one by one, hand by hand, like by their hand. It takes years of time, hundreds of thousands of dollars, and it's just extremely complicated for simpler proteins, right? For very large proteins, it's pretty much impossible to do that by hand, like by yourself. Right. So this is a problem that face biologists because once we figure out what a protein does, we can figure out whether it's a good protein or bad protein, right? So whether this protein, like let's say I figure out the protein that is used for a bacteria to reproduce. If I can find a way to deactivate that protein, I'm done. I'm fine. I'm done. Right. My purpose is over. Or else, let's say I want to create a protein that, let's say, breaks down plastic. Okay, that does some task that I wanted to do. If I can design a protein with a structure that carries out this task, I can mass produce that protein, and now I can like break down plastic, right? This is something that I've said like as an example. It already exists, and that is through AlphaFold, right? So okay, proteins. I've given a lot about details about protein, but again, not proteins, not from the biological point of view. A little bit from biology, just a background so that you understand what's going on, and then like a little bit about what we're going to be learning about. Okay, so the protein data bank. So since the 1970s, we have been trying to get the structures for different proteins. So the protein data bank since 1970 till like around 2020 or so. Okay, till the present time, around 200,000 proteins exist in the protein data bank, right? So if you download the protein data bank, I downloaded the thing. It's around 3 terabytes on your system. So 3 terabytes is your 200,000 protein structures, right? So you download the protein data bank from 1970 to 2020. Keep in mind, 50 years, we were able to predict around 200,000 protein structures. Okay, denaturation of proteins, not too important as of right now. Whatever CASP. Okay, so right now CASP. Okay, so basically, uh, these biologists wanted to find a way to computationally compute, like use computers to compute the structure of proteins, right? So what they created this competition. Okay, the critical assessment of structure proteins, structure prediction. My bad. So they created this competition where people would come up with their algorithms or whatever method they have to predict like how a protein folds. Okay, a protein fold is basically in your cell. Your DNA encodes the formula for a protein, and your cells, your RNA pretty much like starts linking all these amino acids one by one in a long chain, right? So after it's linked in a long chain, it's initially not folded. It doesn't have any structure, just a long chain. However, after it's created, it folds in to reach its lowest energy state, right? We learned it in chemistry, right? A molecule wants to reach its lowest energy state. So it will do whatever it can to reach its lowest energy state. So once it reaches that state, it will, what do you say? That is the structure that it requires. It will always fold into this very specific structure that is used to carry out its process, right? Whatever like purpose that protein holds, it's able to carry out because of the structure. So through any way, using computers, uh, find out how a protein, given the amino acid sequence, it's able to get its structure. Okay, initially they used to use physics-based models that are able to like predict these how a protein folds. However, the first the vast majority of CASP, right? It was started in 1994. However, all the way to like around 2020, every single attempt was a complete flop. They tried using they used initially they tried using algorithms that okay, what we know about proteins, they try to use computer code, they try to code it out themselves to try and simulate protein folding. Did not work. They used physics based models, so like you can have a physics engine that basically replicate how chemicals react or whatever. They tried those systems, it still did not work. And then like they tried AI networks, they also wouldn't work because all these things are very complicated, right? So this is the protein folding problem. Now in comes AlphaFold. Okay, in comes DeepMind, let's say. So Google DeepMind, they just had the success with AlphaGo, right? So AlphaGo, as I said beforehand, AlphaGo is their is their AI model that can beat the human Go champion at the game Go. Right? When Dennis Hassabis, the CEO of Google DeepMind, saw that it was able to do this, he was thinking, okay, we beat this game champion. He has also played another game called Fold It. Fold It is a game created by David Baker, the other person. Remember, Dennis Hassabis was one of the people who won the Nobel Prize. The other person who won the other half of it, there were three people who won. The one who won the half was David Baker. He has another biology lab. But yeah, David Baker, what he did with it is like he created a game called Folded. He was working with CASP and trying to create algorithms. His algorithms weren't very good. There was a game that he created called Folded so that many people can get involved with this problem so that maybe they can come up with their own ideas or whatever. Uh, Dennis Hassabis remembered that game and he was like, oh, what if I like the team at Google DeepMind, right? So computer science engineers, AI researchers that know nothing about protein folding, nothing about biology, nothing about chemistry. How can they possibly create an AI model that can solve this issue? They entered CASP. Their first attempt, they won. However, they won because not because they were good. They won because everyone else was bad. Okay, so CASP 14, they won, but their model was pretty bad, but everyone else's was worse. That is CASP 14. When COVID started, so around 2020, people started this again. So CASP 2020, right? They changed their architecture and they started off with, so they released AlphaFold 2. So AlphaFold 1, it wasn't good. AlphaFold 2, they released, and now it has again, in this time, right? CASP 14 wasn't 2014, right? Around, I believe. Not exactly sure. But yeah, CASP 14 was around that time. It was before the Transformer paper. Now, in 2020, 3 years after the Transformer paper is released, right? Attention is all you need. We have the Transformer, right? So now the Transformer, perfect way to be used over here. You need context required for your the DNA sequence. Like the structure requires the entire DNA sequence to be encoded right into it, because every single atom would impact how the structure folds. So yeah, so this is where we use a transformer. So I can go through the architecture for this as well. And basically, what it does is, I'll give a very short overview. There are videos on it that go into more depth. However, you give an amino acid sequence. It takes a okay, so it goes to the protein data bank. It finds other proteins that have evolved in similar ways. It collects all those like relevant amino acid sequences. It puts them into a matrix. So you call it the MSA. That is the, what would you call it? Yeah, wait, I'll go to the AlphaFold architecture thing. Okay, so yeah, so you have your input. Okay, you get your MSA embeddings. Your MSA is your I forgot the full form for your MSA. Sequence. Okay, but basically it's a matrix that contains like, in short, okay, in from the AI. Okay, okay, I'll not talk about it in too much detail, but I'll talk about it in like an overview. Okay, so like, as in, you can figure out what the researchers were thinking when they created this, right? So your MSA embedding matrix contains the meaning, or like the evolutionary data of a protein across different species, because the protein data bank already has protein structures from like 200,000 examples, right? So it takes all those, so it organizes it in a matrix. Your pairwise features is basically a matrix that the model generates initially to, like, basically the static in your text to image example, right? So it's basically a pairwise feature is sort of structure prediction of your model, which isn't very accurate. You pass that into the evoformer module. Your evoformer module is a type of your transformer module as well, where you have your MSA, you have your pairwise thing. They communicate with each other, and they're able to modify each other in a way that is better. Okay, like that. They're able to encode more data into them, like as we saw in the LLM model, right? Example. So this keeps going through different steps, as we said. I don't know the exact head count in this, but it goes through many different heads. It keeps going through this again and again, and finally, the last pairwise representation that we get is your structure prediction, right? And it's able to use that to generate an image, and that those images are just truly amazing. I'll show you examples later on, but okay, yeah, this is perfect. I forgot I had this. But yeah, so it is able to get you the structures of those proteins. So this is how the protein structure looks like. And you can see these different colors. These different colors show a probability score of how, a confidence score, not probability score, a confidence score of how confident the AI model is that, yes, okay, so if this is a dark blue, it's like, yes, I'm very sure that this is correct. If it is red, it will be like, I'm not so sure, but this is like the most probable outcome. So like that. With this model, they entered CASP 14, and they were able to create, like, they were able to get. See, this is the part where your protein folding prediction actually became good, because the goal with CASP was to get above 90% accuracy, and this is where that started happening. So AlphaFold 2 was able to create protein structures, generate protein structures that were, and many of them were over 90% accurate. And this is the great achievement of AlphaFold 2. After AlphaFold 2, okay, so this happened in 2020. By early 2022, Google released 218 million different protein structures. Okay, so the protein data bank, okay, from over 50 years, it took to just generate 200,000 different protein structures. Now it took maybe 1 year. Okay, and again, not through too much effort. Okay, the model is not that large as well, not through insane amounts of effort. It was able to much more cheaply compute through like models, AI models, the about 218 million different protein structures, which is pretty much everything that already exists, and all of them are already available. One second. Alpha fold database. Okay, so you have your protein AlphaFold structure, protein structure database. You just search up your, let's say, hemoglobin or whatever. Hemoglobin. Okay, let's say any other, any sort of model over here. Uh, oh wait, my bad. Okay, I think they don't. The preview used to be there. I don't know why it's not showing it as of right now. But let's say free fatty acid receptor. But yeah, basically they have released all of this. publicly available for anyone to see. So before you start your experimentation, okay, again, use cases I have mentioned over here. But yeah, they have released all of this. And in fact, if you want to use this model, either you can download it by yourself, you can go to the GitHub, you can download the code. However, I do not suggest that, because to get the full capabilities, you need to download around 3 terabytes of protein database data. However, you can just use AlphaFold server, and you're able to run it, use it for free. Anyone can use it for free to create your own. Let's say you have a custom protein for some purpose that you have designed for some purpose. How you design those purposes, I have mentioned it in the notes as well. How you would design a protein. But yeah, let's say you have a final protein structure. If you have the amino acid sequence and you just want to be sure, like, okay, is this correct? You can just pass it into this. You can get the structure, and you can get this, and you can use the structure to do whatever you want, right? So again, in the notes, I have mentioned in greater detail about how the AlphaFold architecture works. So when you see the evoformer module, that's a transformer module over here. This part, okay, since we already know through scientific research, okay, since with our own actual knowledge, we know the laws that govern these things, we're able to create these features beforehand as well. But before we pass it into the transformer, that optimizes and that's what enables such a high accuracy out of this model as well. And remember, these nodes are of AlphaFold 2. Over here, I have mentioned AlphaFold 3 as well, okay, which adds on to the capabilities of AlphaFold 2, where it doesn't only predict the structures of protein, it predicts ligand structures as well. Ligands are other tinier chemical, like biological units as well, and many, many, many more different things. That in fact, it's so accurate at those things as well. Like, it's a generalist model that has capabilities that rival other models that are created to tackle specific tasks, right? There were models that predict just ligand structures or whatever, and how they interact. It's able to do that as well, because again, the protein structure, this is great. However, we could require more stuff to it, right? How it interacts with its environment, how it interacts with other molecules, all that stuff. That's where AlphaFold 3 comes in. It has a much more simplified architecture than AlphaFold 2 as well. However, AlphaFold 2 is like a pure vanilla AI model, whereas AlphaFold 3 has a lot of human fine tuning as well, trying to like make it as lightweight as possible, how to optimize the outputs, and yeah. So basically, that was the entire goal with AlphaFold. And also, yeah. So I just wanted to know if there were any questions uh, regarding this. I think I'll stop for now. Is there any questions to be asked by anyone? Hmm. Okay, I mean, like, okay, the notes are available online. If you have any questions, go to the notes as well. Then you have YouTube as well. You have ChatGPT, all that stuff. Again, a lot of stuff, a lot of resources are linked. And yeah, I think that's enough. I think you have enough enough of an overview to hopefully, like, get you into the world of AI, as that's the future as of right now. AlphaFold, the Nobel Prize winning AI model, and you have your LLMs, the AI models that we use so regularly for literally everything. LLMs have now replaced even you could say Google searches, right? Where we ask ChatGPT instead of Google. So yeah, that's our task as of right now. Is there anything else anyone wants to say? Okay. Yeah, I think that would be enough, I guess. Uh, Thank you for listening for so long. I'm sorry if I went on too much of a rant into technical details in between. However, some of these things are, uh, yeah, also about the uses of LLMs. My friend will be taking a class a couple of days later as well. So you can use that as well, like using Gemini API for stuff. So, yeah, again, best of luck on your future endeavors into this field and how you use it. I hope this was helpful, and at least I hope that now you know enough to start and get into it. Thank you. Good night. Take care. Also, wait, about the Firebase thing. I mean, uh, we have a certain set of topics, right? If you want, you can ask. I'll ask the GDC members as well. They might be able to help you out with that. But as of right now, the next topic is not related to that. Sneak peeks into the next topic, by the way. But yeah. So, any other questions? Anything else?